Hi everyone. We're going to look today at some radical operations. Now, most of this should be reviewed from Math 10C, but we're going to look at maybe a couple more complicated ones and focus more on algebra. But just to kind of quickly recap what you've already learned, if I start with a radical, like for example, the square root of 405, and I want to simplify it, I start by factoring. That's divisible by 5. When I divide it, I see that's 81. 81 is a perfect square, 9 times 9. I can go all the way down to prime factors if I want, but I don't have to the moment I notice that I have a perfect square. Because this is therefore the square root of 81 times the square root of 5. The square root of 81 is 9 times the square root of 5. So that's a simplified form of this radical. We deal with that simplified form largely so that we can simplify more complicated expressions. So slightly more complicated, if I have something like the square root of 405 plus the square root of 80, I look at each of these individually. Now I already know that the square root of 405 is 9 root 5. But for 80, okay, well that one's 8 times 10. 8 is 2 times 4. 4 is a perfect square, so I can stop there. And then I have 2 times 5. Ooh, I have two 2's and I have the 4. So that's basically like saying I have a 16 in there. Square root of 16 is 4 root 5. Oops, that shouldn't be a plus. That should be or it shouldn't be an equals. It should be a plus. Now that I have the exact same radicand, the root 5, that means I have similar terms. So I can go ahead and add their coefficients, and I get 13 root 5. So that is just a real quick recap of something you should have seen in Math 10 pre-IB. Where we kind of go a little beyond is if I have algebraic expressions with that. So building on this a little, let's say I have 405x cubed y to the power of 9 plus the square root of 80x cubed y to the power of 9. I still have to have like terms in terms of the variables, so I'm going to use the same powers of x and y here. Now, simplifying the numerical part is the same as what I've already done. So the square root of 405 is 9 root 5. But I also have perfect squares in the variables. So x cubed contains a perfect square. X cubed is x squared times x. So the square root of x squared is x. I'm going to put a little asterisk beside that and come back to it. And I had an x left over. Y to the power of 9 is y to the power of 8 times y. Y to the power of 8 is y to the power of 4 squared. So basically, I'm looking for how many pairs of each variable can I create using the number I have. So this is then plus 4xy to the power of 4 times the square root of 5xy. Now, not only do I have the same root in each case, but I also have all the same variables. So these are, again, like terms. And when I add them together, I'm just adding coefficients. So I get 13xy to the power of 4 times the square root of 5xy. Now, I said I was putting a little asterisk on here, and I kind of am, because I cheated a little. I treated this as if the square root of x squared equals x, but it doesn't. The square root of x squared equals the absolute value of x. All right, so that actually means that I should go back here and change these x's on the outside to the absolute value of x. Now, that's a nuance that won't always matter. So in your textbook, for example, it doesn't do that. But technically, it is the thing that is correct. I didn't have to worry about it with the y because the square root of y to the power of 8, technically the absolute value of y to the power of 4. However, because that's an even power, it's already positive. So that's just the same as y to the power of 4. Now, we also have to worry, and we talked about this a little bit with functions, but it's a little trickier when I have two variables. In this case, I know that the overall product of whatever's inside that radical has to be positive. So in other words, that xy has to be greater than 0, greater than or equal to 0. But that doesn't really tell me anything individually about x or y, because x can be negative as long as y is also negative. And y can be negative as long as x is also negative. So they basically just have to have the same sign. So we're good enough just to add in the fact that the product xy has to be greater than or equal to 0. All right, we can also deal with divisions. And so if I have something like the square root of 75x to the power of 5 over the square root of 48x squared, I can simplify each of these radicals individually, but in this case, it's actually easier just to treat it as one square root and simplify the fraction first. So I'm going to simplify the fraction first because then I'm dealing with smaller numbers. In either case, I do deal with the factorization. But now because I know I have a fraction, I'm looking for common factors. And a common factor between 75 and 48 is 3. So if I divide them both by 3, I get 3 times 25, x to the power of 5. And I get 3 times 16, x to the power of 2, which allows me now to cancel out the 3. And conveniently in this case, both 25 and 16 are perfect squares. Also, I know with the x to the power of 5, I can cancel it with the x to the power of 2, and I get a 3. So now, square root of 25 is 5. Square root of 16 is 4. And I have the square root of x cubed. Well, x cubed is x squared times x, so I have a perfect square that I can pull out, technically absolute value of x, times the square root of the x that is left over, because I have an odd power of x at the end. Now if I think of restrictions, well, x has to be greater than or equal to 0. However, because I did have an x in the denominator, x cannot equal 0. It doesn't matter that I canceled it out. And the reason it doesn't matter is because there is no such mathematical operation as canceling. Canceling is not a mathematical operation. What I've really done is divide. So when I say I canceled the 3, really what I've done is I've divided the numerator and the denominator both by 3. And when I say I've canceled the x squared, really what I've done is I've divided by x squared. But I can't divide by 0. So if the x were 0, I couldn't have canceled it because I couldn't have divided it. So even if it gets canceled out, it counts, which means that when I combine these two restrictions together, I get the overall restriction that x is greater than 0. It cannot be equal to 0. These sorts of simplification rules still apply with more complicated algebraic expressions. Now, I'm going to write one that isn't really that complicated, but it is slightly more complicated in that it is no longer monomial. So if I have the square root of 9x minus 45, it's not a monomial anymore, but I start in the same way. If I'm wanting to simplify a radical, I factor it. So I factor. 9 is a common factor, and I have x minus 5. I ask myself, are any of these factors perfect squares? Well, yes, 9 is a perfect square. So I have 3 square root of x minus 5. And then I can deal with restrictions. X minus 5 has to be greater than or equal to 0, which means x is greater than or equal to 5. If I have a quadratic, well, I still go to factor. So let's say I have the square root of x squared minus 2x plus 1. Well, this one factors and it actually is a perfect square. So the factors of x squared minus 2x plus 1 are x minus 1 and x minus 1, which means I have the square root of x minus 1 squared. But remember, square root of something squared isn't just that something, it's the absolute value of the something. So this is the absolute value of x minus 1. There are no restrictions here anymore. Because this is a perfect square, it was always going to be positive. So here, x is an element of the reals. The other thing that we looked at last year was rationalization, or last semester, sorry, was rationalization of denominators. So let's say I have something like root 3 over root x. Neither of these can actually be simplified, and I don't have any common factors, so I can't simplify the fraction. However, we do not want roots in the denominator of the fraction. Technically, this isn't rationalizing anymore because I don't know if x is a rational number, but I don't want square roots in the denominator. So I'm going to multiply numerator and denominator by the square root of x, which leaves me with the square root of 3x divided by x. My restrictions in this case come from two places. X has to be greater than or equal to 0, but also x cannot equal 0. So when I combine those, x is just greater than 0. Rationalizing when I have something a little more complicated, so binomial. So let's say, for example, I have 1 over the square root of x plus 1. Now I can't just multiply by the square root of x, because when I distribute it through, I would just still end up with a square root in the bottom. So in this case, I have to multiply by the conjugate. I'm multiplying by the square root of x minus 1. But that means I have to multiply by the square root of x minus 1 over the square root of x minus 1, so that in reality, I'm just multiplying by 1. Now in the numerator, that distributes just 1 times root x minus 1 is root x minus 1. In the denominator, because I'm now multiplying through a binomial times a binomial, I have 4 multiplications to do. Root x times root x times negative 1, 1 times root x, those two are going to cancel each other out because I'll end up with negative square root of x plus the square root of x, and then 1 times negative 1. So the only 2 multiplications that actually matter here are root x times root x, which gives me x, and 1 times negative 1, which gives me 1. So this is my simplified fraction. Now, I have 2 spots where restrictions are coming. I have the fact that x has to be greater than or equal to 0, which comes from the fact that I have a square root in there. And I have the fact that x cannot equal 1. So in this case, x can be 0. If I substituted in a 0 here, in the original fraction, I would get 1 divided by the square root of 0 plus 1. Well, that's 1 divided by 1. There's no problem there. There's no division by 0. On the other hand, once I've simplified it, that's a problem. It's not a problem in the initial fraction. In the initial fraction, if x equals 1, I get 1 over 1 plus 1, 1 over 2, perfect. But because I've now manipulated, I end up with something slightly different. So it's an equivalent rational expression, but it's not exactly equivalent because it does have a restricted value I didn't have before. But now if I combine these two things together, I have values of x such that x is greater than or equal to 0, but x does not equal 1. I gotta actually write the 1, not just say it. And x is an element of the real numbers. So that's some basic review. I think most of it is stuff that you've seen already, but you should practice it. This is in section 5.1 and 5.2 of your Pre-Calculus 11 book.